Okay, all right. So, okay, good. So any questions about the midterm? I haven't graded yet, but any question on the format or on the length and time? So the final will be sort of almost exactly the same format. Yeah, be very similar to the midterm. Well, be comprehensive in the sense that you have still, so we'll de-emphasize the first part of the class. Although after type 4, we'll be doing some probability and statistics, then the 1 power will come back, and the cube will come back. Like that's still an important relationship. But it won't be so heavy on things like,
Shown up, but all of us ended up having to sign on to Zoom to see his slides to connect back to the projector. Professor is lecturing and all of us are also on Zoom.
Yeah, okay, so hopefully it's good now. Came back. Okay, all right. So we'll start with type 4. So this is the last type of wind turbine we'll have. So type 4 is sort of taken type 3 to its sort of natural conclusion, right? So you think about type 3. Type 3 still have 2 paths. So you think about type 3, you have a generator, you have a connection to the grid, then you have a power electronics. So this is the AC-DC bridge. Capacitor, AC. Okay, all right, so type 3, if you have a generator, basically you have 2 paths for power to flow. And then type 4 says that, well, so why bother with 2 paths? Okay, so the problem having 2 paths of power flow is that you have 2 potential places of failure. So one is this capacitor, another is this gearbox. They're both so the gearbox is very difficult to maintain. The capacitor tend to break. Okay, so type 3, because the power flow in reality will be, this will be not that much smaller than this path power flow. So now you have 2 potential things that could break and make maintenance more complicated. But the idea for type 4 is, well, so let's just forget about this path. Okay, so we're not even going to bother with this upper path anymore. We can just look at through this power conversion stage. The benefit of just looking at this power conversion stage is basically now I don't need to maintain the frequency. Okay, I can take whatever the wind speed is, turn this generator at 60, not hertz, but let's say 60 RPM. I can do that. Since I'm doing this conversion anyways, I can set the grid frequency here. Okay, so that's what type 4 does. So type 4 says, okay, let's not even worry about the grid. Let's just take a synchronous generator. So if you're a synchronous generator, you don't need an external frequency. You have a magnet that's turning, so whatever that frequency is, that's fine. Let's just do that. So let's just. Okay, and then this connect to the grid. Okay, so that's type 4. Here you have a basic synchronous generator. So this is pretty much the generator that everything else uses. If you're gas, if you're coal, you're nuclear, use this synchronous generator. So here we are just going to take this generator, convert it to DC, convert back to AC to get the frequency correct. Okay. So as output here, this is roughly 60 hertz. Input here, this is variable speed. This is sort of variable speed. And this is typically fairly slow. For example, this is 60 RPM.
Eliminates the gearbox.
It's eliminating the gearbox. There's no gearbox. You don't need a gearbox for this because you're not doing any mechanical speed conversion. Right? There's no mechanical speed conversion. So again, this is whatever wind speed is. Okay? It's determined by wind speed. You don't need a gearbox. So this is currently almost all turbines new turbines are this type. right? Where you don't need a gearbox, and your main power conversion comes from this power electronic boxes. So of course, it took a while to get from this point to this point, because you have to wait until you can pass, let's say, 5 megawatt of power through these two stages. Okay, so these are not small converters, right? You basically, let's say this is a 5 megawatt turbine, you have to have 5 megawatts go through this converter, this capacitor, this converter comes out to the grid. So all of these are, again, expensive and components, but the main benefit, again, there's no gearbox. You get rid of the gearbox. So the maintenance is easier. Right? So you don't need to maintain it. You don't need to, change the oil, look at the bearings in those kind of gearbox. Things still break, especially that capacitor in the middle. So things could still break, but you don't have to do this kind of monthly maintenance or weekly maintenance compared to type 3. So reliability now is basically a factor of how good that DC to DC bridge in the middle is. Okay, if that thing is reliable, this whole thing, again, not much can go wrong with this. If you have problems with that power electronic stage, then nowadays you're swapping a new capacitor. You swap a new capacitor with this. Okay? So this is the idea of type 4. So a lot of what goes in type 4 is into the power electronics. Right? That's where the action is. So that's all the scope of this class. This is too high power for us to cover. We won't be able to cover the the actual challenges in this designing this power electronics. And this is actually higher power than most of the power electronics you'll see. There's very specialized places that deals with this megawatt level power electronics. Okay? And things you don't think about now becomes important. For example, don't destroy the material. Don't destroy it again, basically, in this kind of power electronics. Again, these are specialized places that deal with this. We are not going to spend too much time on this, but so what we'll do is we'll always pretend this is just an ideal thing. Right? We'll pretend this is ideal, and then think of this just some transmission line. Although that's good enough from a system modeling perspective. If you actually work on type 4 turbines, most time you'll be working in this two blocks. It's not right. So, but for us, we'll often pretend we'll so what we'll model this as, well, we'll just model this as a synchronous generator to a grid. So we'll model this as this is something running at close to 60 Hz, connected directly to the grid, and not worry too much about this intermediate stage. So when we do protection, we'll look at this intermediate stage again. But for now, it's not terribly important in a lot of calculation we'll do, which makes type 4 again much simpler than other types because of this option. Okay, this goes back to 351 generator transmission line grid. So the equations are simple now. Okay. Any questions with the concept of type 4? Okay, so the trend again nowadays is always move as much as possible into a solid state device. They put everything to solid state devices. Right, so remove mechanical drives. So don't put so remove as much as possible conversion from mechanical to electronics and deal with electronics, not mechanical drives. So if you make this assumption, it's just a 60 Hz machine, then we go back to our old synchronous machine. This is just synchronous machine we have all seen many times before. Is you have a stator, you have a rotor, you have exciter. So what does wind do? You can conceptually think wind is rotating this thing. You have a magnet, you rotate this magnet at 60 Hz now, right? Because power electronics, we're going to assume this is rotated at 60 Hz. You have a three-phase machine. So the three-phase nature is actually very important. So if you actually look at how you design this electronics, it's very important to have a balanced three phase. So there's a lot of effort spent again in this conversion steps to make sure you have a balanced three phase. Here we're going to assume that we're always operate at balanced three phase. Okay, so have some three phase operation, it's always balanced. And the benefit of this is, well, if you have a balanced three phase, again, there's no net voltage or net current flow. Everything cancels. Okay. So now the synchronous speed, again, the synchronous speed is NS, the sort of, you have to determine the number of poles against the frequency you're actually rotating at. For us, again, we're going to assume that this is operating as a grid synchronous frequency. Okay, so everything is done such that we are just directly interfacing to the grid, and we have this frequency. So drawing this again, right? So this is our picture of the type 4. This is called direct drive, again, because you don't have a gearbox. You're directly driving from one to the grid, getting rid of the mechanical gearbox in the middle. Okay, so you have a variable frequency, you have a terminal bus frequency, you have some transformer, and this connects to the grid. Okay. So if you look at it, what does it look like? This may be more interesting as a picture. So this is a picture of what the turbine looks like. So basically these, so you attach, this is the hub. So the blades are attached here. This thing turns, and this is very sort of actually, it's sort of skinny because you don't have a gearbox. You know? Okay, so this directly turns. This is the generator. That's a power electronic stage, and the power comes out this way. Okay, so if you compare, for example, something like type 3 will be much longer because of the gearbox. And this, because you get rid of gearbox, is sort of a skinny looking thing. Right. So this is all the three electronics right here. You directly drive it. It's a skinnier machine that we have. Okay. So now we can look at power flow. So we'll do some calculations. Again, the equations will come out simpler. The equations for synchronous machines are really much simpler than for induction machines. Okay, because you are setting the frequency. So you don't need to compute the slip. There's no this sort of slip business, anything of that. As you're directly setting the voltage, make all the calculations easier. Okay. All right, so this is our network. The model we have again, what we'll be looking at is the following thing. What we look is all this part become a single voltage source. This is V out prime. Okay. All this becomes, we can think of as a voltage source now, after the conversion, after the transformer, all that. Okay. So how does this connect to the grid? Well, it's connected to the grid in the following way. We have one reactance. This is a transformer reactance. Okay, so we still need a transformer. This has to have a transformer that sets as a voltage. So this is a transformer reactance. This is plus the line reactance, right? This is always there. We have a transmission line. Line reactance, and this is our grid output. Okay, so this is our model now for the type 4 turbine. So the turbine's job, the generator's job, is to give us this number. Then we can compute power flow this way. We can compute power flow. So again, this is very different than the induction machines. In induction machines, everything is driven by slip. You have a slip, you have to compute the current, and then you compute the power. Here, you directly get this voltage source. Okay, so all this gives us a way to control this voltage source. You can set your voltage and angle to provide the active and reactive power you want as the grid. Okay, so this is the model. Okay, so because we have a transformer, so V out prime, right, at this terminal, right here, V out prime, this is V out N1 over N2. So you still have a N1 over N2 transformer ratio. So one question is, why don't I just do this after the converter? Why bother have a transformer? There seems to be two steps here. So I'm converting voltage anyways. Why am I then using a transformer to step this up? Why not just do this whole thing in one shot? So why is that? Why is it cheaper to have a transformer? Right, so transformer is simpler because if you do the up voltage conversion, so what happens when you do up and down voltage conversion? What happens in the converter? What do you have to sort of store in the converter to do this up down voltage conversion? Right, you have to store power in the converter. So remember a buck converter. What is a buck or a boost converter actually? Not a boost converter. What does a boost converter do? It stores the energy in the inductor and capacitors, right? Then it releases the energy based on switching. If this is 5 megawatt, you need to think about whether you want to do that or not. Okay, so you want to think about how much energy you want to store in the converter. Whereas a transformer does store energy, but that is much, much simpler because the metal core itself, through the magnetic field, the energy is constant through the magnetic field, right? You're just converting voltage and current. Whereas here, you have to be more explicit with energy storage. Again, this is megawatts, right? So think about the size of inductor capacitors in this to store that. Okay, so that becomes challenging. So that's why you do a transformer. So if you know, if you can control the voltage here, the transformer is much, much simpler to use. It's not as flexible, it has sort of very set voltage operation level. But once you keep that, then transformer is much cheaper. So we, a lot of times we still have a transformer. But, yeah. Right, yeah, so transformer also give you isolation. Transformer also give you isolation between the two sides. So it's a good transformer to have in between those two. So that's why VL has a prime. That's why VL sort of has a priming. It's a transform quantity. Although a lot of times we won't exactly care about the transformer ratio, just go with output voltage. Right? Yeah, so now if you look at this, you can sum, of course, you can sum the reactances. So this is X, Vg, really gets us to a very simple circuit. X is the sum of the transformer reactance plus the line reactance. And what we want to compute is we want to compute the complex power delivered to the grid, right? The active and reactive power delivered to the grid by setting up a voltage VL prime. So that's what we want. Again, this is Vg times current conjugate. So this is P plus JQ. Right? Any questions? So one thing again to remember is for type 1, 2, 3, the resistances in the lines are important. You cannot have actually a induction machine without a resistance on the rotor. The rotor resistance are important because it's a 1/S divide. Okay? Here we don't care anymore because there's not a R/S. Then because R typically here is much smaller than X, we just ignore it. Okay? So we ignore the active power losses along this line. Important. So whatever we send in, active power actually comes out this end. So that's often a very useful fact to remember. There's no active power loss on this line. Okay, so the generator, at least if you look at this diagram, is 100% efficient in terms of active power. Okay, so that's a useful fact to remember. All right, so let's do this calculation, which we have done for the type 3, looking at the other path, but let's just do this again. All these equations are actually important equations for power flow and for stability analysis, which we'll do later. So if we do this calculation, we have the current. This is V out. I is V out minus VG over X. So VG is almost always the frame of reference for us. So that's a zero angle voltage for us. Okay. So V out is not, V out has some angle. So we can write this as V out prime cosine of the angle plus J sine of the angle minus VG, which is angle 0, Jx. This is our I. Now we multiply I, conjugate of this thing with the grid voltage to get active and reactive power. So what we do is this is VG. Again, there's no angle is 0 for that. I star. If you multiply this thing out, we get V out prime VG over X sine delta plus J VG over X V out prime cosine delta minus VG. So this is right. So if you do this multiplication, you collect terms. This is the thing you get it. So again, we'll go back to our very familiar result of active power depend on the sine of the angle, reactive power mostly depend on cosine of the angle. Okay, any questions about that? All right, so this is our power flow. So this is our power flow. Why do I have two pictures here? Okay, so again, these are the important equations to remember, highlighted here, right? So, and one thing that we often write is we write V out prime VG over X as P max. And this is something we like to write. So one, this has a right unit. This is V squared over ohm. So this is voltage squared over ohm. So that's the unit of power. And what the reason we call this P max is sort of evident because the largest this value can be is 1. Okay, so this the sine as largest at power 2 is 1. And this is the maximum amount of power you can deliver. Okay? The max power depends on your voltage output, the grid voltage, and the reactance you have on the line. So that's why you see this notation a lot. P max times sine theta, this is sort of constant. All right, so then the interesting thing is to do a small angle approximation. So all these equations, although it looks simple, for this sort of one generator connect to infinite bus here, if you start thinking about a network of these things, then the sine and cosine actually makes your life difficult. Okay, so this is not linear. For one generator, it's okay because just one angle that you can solve. You can even graph this if you want. When you have many things together, this makes your life difficult. So a lot of research actually in this is how do you deal with this sort of nonlinear terms. Okay, but one way to deal with them is to think of a small angle approximation. Okay? So why is the angle small? So before talking about small angle approximation, we need to think about why is the angle typically small in power. You actually hear that a lot, like, oh, the angle between two buses is small. Why? So small angle approximation just means linearize these equations around 0 when the angle is 0. We can ask, why should I linearize around 0? Why is the angle not close to, say, pi over 2? Why is the angle not 45 degrees? Why is the angle something else? Why is the angle small? Angles are typically small, typically less than 5 degrees in the system. It's very, very rare to see an angle that's for double-digit degrees. You need to wait for some unusual condition for that to happen. But why is that the case? Right. So that is the case. Again, if you look at this equation and you think back to for Tesla and Edison, right, when they're talking AC and DC. So the reason to have AC is the voltage are high. Means the losses along the lines are low. Right? That's sort of the whole point. As you want small current flowing on the line, you have smaller loss. So if you look at this equation, the voltage is a large means these are large numbers. These are large numbers. So to drive power flow, if these are large, you make them large enough such that you have small angles, such that you have small current, but that will mean that this angle is small. Okay? So it's beneficial to the grid to have high voltages, to have smaller losses. As a consequence, you have small angles. Okay? We don't offer very large angles because the system, the AC system was precisely designed to offer a high voltage. Right? So that's where we spend all this effort making high voltage things. So it's not to make them that simple. Just this is the way it comes out. If the voltage is large, then the sine delta term has to be small. Okay, so small angle approximation means that as sort of close to 0, you can think of less than 5 degrees, something like that. This is a rough number you'll see. 5 a little bit small, I guess less than 10 degrees. Okay, so small angle approximation makes all these equations actually quite neat, because so if the angles are small, sine delta becomes delta. This is sort of approximately delta. You do a Taylor expansion. This is the first term in the Taylor expansion. And then the active power flow becomes P max times delta. So if you look at this term, it's the P max times sine delta. Angles are small, then just P max times delta. And now this is a linear equation. If you have a system of those things, if you have a linear system equations, your life is infinitely simpler. Right? This is a linear system. Okay? All right, so the more interesting is, now what is cosine when the angles are small? So sine of a small angle, sine of small delta is delta. What about cosine? One, right? 1, right? So cosine, the important thing is still do a Taylor expansion. Cosine is 1 minus delta squared over 2, right? So if delta is small, delta squared is sort of doubly small. We don't care about that term. We're going to throw that away. And then what happens for cosine is, so this is 1 minus delta squared over 2. This is really approximately 1, a small thing. And then you have a very interesting equation for Q now. This is, so what does this say? Right. So if you make this as roughly 1, there's no angle anymore in this. So what this equation says is at approximate level, the reactive power flow and active power flow are decoupled. Because active power flow is controlled by the angle. Reactive power flow, there's no angle. The angle completely disappears from this equation because of this approximation we make. So that's why in practice, you can often just think about active power flow as adjusting the angles. Right? So when you solve power flow equations, for the folks who are taking 454, for the folks who are taking 458, you may have things when you solve power flow equations, let's assume the voltage are constant, assume the active powers are changing, let's solve for the angle. The question is, what about reactive power? Well, at this approximation, reactive power doesn't change. It's the same reactive power we had before. So that's why you can treat them too as the first approximation independently. Okay? Active power flows based on the angle, reactive power is sort of roughly constant from this equation. Okay? Roughly constant. Okay, so that's a good sort of approximation to know. Okay? In this class, again, because we're just looking at one generator connected to the grid, so you often just ask directly to deal with this nonlinear equations. Because again, if just one generator, it's not too hard to solve these. When you're working in a system, these are all the sort of very common assumptions we'll make. Questions about these assumptions? So this is actually a key assumption. If you ever work in large power systems, you'll come across this again and again. And then you come across you have a lot of operation. And that's with underlying assumption that active power and reactive power can be handled separately. Okay? The reason they can be handled separately basically comes from this. Okay? That's sort of how the Taylor expansion of sine and cosine works out. Okay? Just as the cosine does not have a linear term. There's no deeper sort of physical mystery. It's just the way cosine works. The way the Taylor expansion of cosine doesn't have a linear term. If this had a linear term, this would depend on delta, but does not. Okay. And this again tells you it's very easy to make active power 0, reactive power non-zero. I can make delta 0. This thing has some number. That's why, again, a synchronous generator is nice. It has this sort of two decoupled control capability. Type 3 does not. You will not get this nice equation for type 3. You'll get this for type 4. Okay, so that's why type 4 is again nice. Questions? Okay, so so the equations here again are not very hard. We have a lot of intuition built from the equations, looking at simple equations. Again, real power control. How does this work? This is so you basically, if you draw the delta axis and the power you can generate, well, what this looks is basically this is some sine curve, right? Some sine curve, and if you want to deliver a certain amount of active power, let's say to the grid, that will directly gives you the angle you should be operating at. So this, if you pick a power, you operate at some angle. Okay. So later, after this class, we will see why you should pick this angle and not this angle. Okay. So the idea is because there are two angles you can pick. So if you directly solve the equation, the two possibly entirely okay equations, entirely okay solutions that will solve the equation. Always pick the smaller one. Always pick the smaller one. And we'll see why. We'll see why you should always pick the smaller one. That has to do with stability. But that's just something to remember if you do a homework question. If your calculator gives you two answers, it's up to you to pick the one that's closer to 0. Okay, don't pick some angle that's 150 degrees, right? So. No, so the small angle, right? So there's a reason why we want to operate here. There's a reason why I want to operate here. Yeah. This is not too bad for a small angle operation because this is also roughly. It doesn't destroy the small angle approximation. It's linear here. It's linear here. It's sort of flat here. But this has to do with stability. You just want to pick this solution. And so again, if you're an operator sitting in a control room, if your angle ever gets to say 20 degrees, there'll be warning lights flashing all over for large angle. You see a lot of red lights flashing for this. So that's something to pick there. Okay, so this sort of equation we have. Right? So let's do an example without these equations. Right. So let's say we have a type 4 turbine. There's generating 2 megawatts from wind. I have a synchronous reactance inside the generator, that's 2 ohms. The line is 5 ohms. The grid voltage is 13.8 kV. Right, so if I have a system operating at 5 degrees, compute what the power is, right? What is the compute what is the output voltage I should set if the angle is 5 degrees. The pull-out power means the maximum power. So pull-out means this is Pmax, the maximum power you can have. So this is an example of given. Right, this is given the angle, figure out what is the voltage. Okay, so this is saying that this angle is 5 degrees, or given. That x on the transmission line is 2 plus 5, 7 ohms. I have 2 reactances in the system. I know the grid voltage compute the VL. Compute VL prime. So the way you can do this equation again is to remember, right? So, there's enough information. Well, again, to remember that there's no active power loss along the line, right? So 2 megawatt from wind is the same as 2 megawatt delivered to the grid in the system. Okay? So if you look at all these equations, these are in terms of power delivered to the grid, right? PG, power delivered to the grid. But because we're talking about active power, the power from wind is equal to the power delivered to the grid. There's no losses. Then that gives us a simple equation to use. Right, so we have Vg, VL prime over x sine delta. So we know right? So you can turn this around. This gives us VL prime equals to x PG Vg sine delta, right? So isolating VL prime, then all the numbers we know, right? We know what is the power, we know what is x, we know the angle, we know the grid voltage. Plug all this in, you get 7.46 kilovolts. This is line to line. Okay, so this is our line to line voltage. So for this kind of problem, if you ask to compute voltage, if you don't say anything, again, the assumption is the voltage is in line to line. If you compute per phase, that's completely okay, but you have to say it's per phase voltage. Right, so here, for safety, you can write line to line voltage for this one. Then P max, this is, right, so V out, G over X. So to be perfectly safe, this is 3 because 3 phase times all 3 phases. So this is 11.64 over 3, 13.8 over 3 over 7. This we get is 22.95 megawatt. Okay. Just again, remember 3 phase. So there's a 3 if you're talking about per phase voltages. Okay. No questions for this? Okay, so this is one question we have for active power. You have a more difficult question if you're given the reactive power flow. Because reactive power is not conserved on this one. You lose some reactive power on the line. Okay, so the active power equations are simpler to deal with. Okay? So that's one thing to remember for type 4. So active power, then we can talk about reactive power, right? So the nice thing about reactive power is, again, if you look at those 2 equations, this is VL prime. Okay. So reactive power basically is the sign of reactive power is determined by this sign, whether this is without a code. Okay. So this is reactive power determined by the sign of this term inside of it. So this is greater than 0 if this term is greater than 0. This is smaller than 0 if smaller than 0. So you have sort of a fair bit of flexibility to find out, to adjust for reactive power. Right? So, okay, so again, look at this equation. So suppose you want to adjust your reactive power, right? Your generator, so you can control two numbers, right? Should you try to change VL prime or should you try to change delta? Let's say for reactive power. VL, right? Again, because cosine is just not very sensitive to delta. Okay, it's just not very sensitive to the value of the delta. So for reactive power, it's much easier. Control V out. It's much more sensitive to this value. Okay, you control V out. Then how do you keep active power flow, right? So let's say you want to keep the active power flow constant, then you can change delta to make active power flow constant. So again, you see this sort of decoupling between active and reactive power. Reactive power mostly depend on voltage. Active power mostly depend on angle. This sort of nice decoupling between the two. Right. So okay, so this is the sign of reactive power. So if you draw this, again, reactive power can be both positive or negative. Right, so this is QG. So if you draw this delta, you basically have sort of some curve like this, right? So it can operate at both sort of positive and negative values. And there's no reason why it has to be positive or negative. So this is unlike active power, where a generator has to supply active power. Reactive power could be both positive or negative, depending on the value of V and delta. All right, so let's do another example. Again, the equations here are fairly straightforward, not much more to say about the equations. Right, so all your equations for type 4 are much shorter than equations for type 3. So let's do another example. Let's say, have some power captured by the blade, it's 1.3 megawatts. The turbine, so the generator cell itself is 77% efficient. I have output voltage. I know what VL prime is, 15.2 kV. I know the reactance. I know the grid voltage. Compute the real and reactive power delivered to the grid. So this is a typical example. Well, this example again is asking you to do the following. So to compute real and reactive power delivered to the grid, what you do, so everything else you know the voltage, you know the reactance, you don't know the angle. Okay, so this problem is basically asking, can you find the angle? And the way you can find the angle is you know the active power. So this is a pretty typical way the question goes. From the active power, find the angle. From the angle, then find the reactive power. Okay, so you look at this equation. It may seem to you that you don't have enough information somehow to determine this. But a good thing always remember is this active power after this efficiency is completely delivered to the grid. Right? All the active power is delivered to the grid. So there you will have enough information to find the angle, then you find the active power. Okay. Right, so the strategy for this type of questions is use active power to find delta, then find Q. Right? Use P, find delta, then use delta to find Q. That's a strategy to solving this kind of problems. Okay. All right, so that's the problem we have. So if you look at the solution, again, we know VL prime. This is 15.2 kilovolts, X is 10 ohms. The grid is 15 kV. Okay, so let's compute. Let's first find the angle, then find the active. Right, so the active power, the power delivered to the grid, the power captured at the blade times the efficiency, so 1.3 megawatt times 0.77, 1 megawatt. So that's the power to the grid. And then from this, we can use PG is equal to VG, V out prime over X sine delta. This is again the equation we have. So we know PG, we know VG, we know V out prime, we know X. Plug in, find delta. Delta is 2.5 degrees. Okay. Again, so be very careful, pick the smaller value. Okay, so determine how your calculator is set up. There's two possible values for this. Pick the value closer to there. Pick the value less than pi over 2 for this thing. Then we have QG as VG over X, VL prime cosine delta minus G. Plug everything into this number, we get 278.3 kilowatt reactive. Okay. Any questions for this problem? Yeah, go ahead.
What is there traits for you to give an efficiency? Do this order of calculation. Where does the efficiency come from?
Oh, so your generator is not perfect. Your synchronous generator is not perfect. Yeah, there's some efficiency there. Right. So you have some blade. Yeah, that box. Yeah, that box. Yeah, yeah, you have that. That doesn't need to be perfect. 77% is a little bit low. Nowadays the efficiency is much higher. But there is always some loss from the power capture blade to the high voltage end of the transformer. There's some loss through that chain. So that's the efficiency then. Okay. Any other questions? Okay, yeah. So the equations again here are, this is for most of the equations for type 4. It's for us, it's just a synchronous generator sitting happens to be after a blade of the wind turbine. Okay. So let's take a break. Then after that, we'll do protection. Then after that, we'll look at some stability issues. So why does this angle have to be small? And what happens if this angle is too large? Okay, so let's take a 10-minute break. We'll come back at 9:30. Then we'll do the stability. Okay, so for type 4, then the next is protections, right? The protections again will have choppers and dynamic resistance, so it's very similar to before. Well, the idea is you want to protect the capacitor in the middle. And the whole thing is do not break that capacitor in the middle. So the chopper, the idea is this capacitor is very important for this whole thing to work. You don't want to break this thing. So you create another path for power to flow through. Right? So if you need to dump power before you get to this stage, you create a parallel path for power to go through this resistor, so you save this capacitor. Right? So why is this capacitor important? Right? I've been saying this, but like, why is it important to have a big capacitor in the middle of these two?
Large volume of DC.
Right? So one is, right? So you basically what you want to create, the thing coming out here is never perfectly DC, right? This is smoothing that. Right? So larger the capacitor, the better the voltage looks. Right? An infinite capacitor holds the voltage exactly at a value. So the larger it is, the more constant the voltage is. So without this capacitor, actually this may not function. Okay, this sort of holds everything together. But because again the power is very high, your capacitor is for a lot of large energy is flowing through this capacitor, being sloshed around in this capacitor. So that's why it tends to break. Right? That's why sort of the material is important. And so this is, again, large capacitors are very expensive. So this capacitor is important. You have to have this sort of decoupling capacitor here, right? So in this kind of application, we're not that constrained by space. They just show you a huge capacitor. If you are doing things like microelectronics or you're doing embedded, you're space constrained. A lot of your issue, like a lot of the art of designing circuits is how do you not use a huge capacitor? Right? How do you control everything so you don't have to use a huge capacitor? We are not in that. We typically don't have that issue. We're not that space constrained. So you can put a large capacitor and just make sure you protect it, but so nothing happens to this capacitor. Okay, so here we'll look at some equations, look at how much power you have to dump through this resistor for things to work. Right, so one way to do this is to compute how much power energy is actually stored on average by the capacitor. Right? So it's storing some energy for operation. So the energy stored by a capacitor is half CV squared. So you may or may not remember this from circuits, but this is the energy stored, capacitive energy stored, right? So C is the capacitance, V is the average voltage or the operating voltage in this DC link. So this is your average capacity, and you don't want to exceed this value too much when you have a transient. You don't want to go over this value too much, because this is design. When you have a design spec, you design the value of this capacitor, the heat tolerance, everything, assuming you'll see this much energy in the capacitor. So you don't want to exceed this number, the steady state energies. Okay, so that's the value. So the maximum allowable limit, basically what you have to do is, well, there's some max this voltage can go to. There's some max this voltage can go to. What you want is you want the gap between the maximum value you can ever reach, subtract the operating energy. There's some difference here. Okay? This is your max, this is your operating voltage. You want this gap, you want this this excess energy to go through your resistor. This is the goal of the chopper circuit. Okay? So again, so the reason I have this max allowable limit is if it gets higher than this, I can open a breaker, I can turn this whole thing off. Okay, so this is not arbitrarily high. But let's say if this just goes 10% higher, I may not want to just open everything on the circuit. I still want this to be operational. So I just survive this. The way to survive it is to dump through of this VR, dump through this resistor. Okay? You want to get rid of this through this resistor. Okay, so that's the whole idea, right? But again, this is not a substitute for the breaker. This is rather sort of right through fast transients in the system. If there's a fast transient, the voltage shoots up a little bit. Can I get rid of this energy, excess energy in the circuit? So what this gives you is there's a way now to control the switch, because so the way, right? So you have some time you want to dump the energy for. You have some voltage that's being set up. So you can, what you do is you control the switch, right? So you control the duty cycle K to get rid of the energy. Because the resistance is a fixed value, that doesn't change. So the way you have a varying resistor is controlling the duty cycle. Right? So by controlling the duty cycle, you can control the effective resistance through this line. Right? And the assumption is that the switching frequency of this switch is high enough that you can just look at the average value of this resistance. Okay, so in real time, of course, this is sort of on-off switch. So sometimes you see the entire resistor, sometimes this is open. But we're going to assume this will switch fast enough, right? This will switch fast enough, much faster than, say, the time constant of this circuit, such that you appear as an effective resistance. Okay, so that's important. Right? So you have a lot of switching, just we're going to assume that this will be fast enough. Then this RC circuit, that's the assumption. And so if switch is fast enough, from the capacitor first wheel, it looks like some resistance value, some resistor. And then what we can do is we can compute sort of how fast that this thing needs to switch. Okay, so there's the idea of how fast I have to switch, right? So now let's look at different things we have to balance. Okay. What do I have? Well, I have an energy, so I can dump through this resistor. This is VR squared over RCH times T. Right? So what is this VR, right? What is the effective voltage I see here? If I take the resistor to be RCH, what is the effective voltage? Well, this VR basically is the duty cycle times the voltage across the path, right? So I have an average fraction of being on with fraction of K. So that makes the voltage look K times the maximum DC voltage. So K is again the duty cycle here, or the duty ratio here. Then the idea what I want is I want to solve for K, such that ER equals to the right value. Okay, so what I want is, I want ER. This is the amount of power I want to get rid of, is the amount of energy I want to get rid of, this energy. This is equal to VR squared RCH times T. This is equal to K squared VDC squared max squared over RCH times T. Right? Okay. So I want to get rid of, right, so this is energy building up across time T. I want to find a K such that I get rid of this much energy. So that's okay. So we're going to solve for K. Everything else, you can think of everything else being given in the system. I have a transient that lasts for this long in time. Let's solve for K. Okay? So that's a way to think about this right now. If you solve this equation, you get K is equal to CRCH over 2T, 1 minus VDC max. Okay, so that's the equation for K, right? So the square root comes because you have a K squared here. Collect everything else together, you got this equation for the duty ratio K, right? For the, so this is, so hopefully this will be a number between 0 and 1. You have to actually size this thing out correctly for this to come out between 0 and 1. Right? So if it's not between 0 and 1, then you're in trouble. But so all of these values are sized such that this K will be between 0 and 1, and that's how you control this. So this is the chopper circuit to spend energy. So we can do a very simple problem, putting all these numbers into look at some sort of reasonable numbers here. So let's say I have a type 4 turbine. This whole thing is rated at 1,000 volts. I have a 100 microfarad capacitor. The chopper resistance is 2 ohm, and during a transient, my bus voltage went up by 10%. This lasts for 1 millisecond. Compute the K, compute the ratio K. I need to dump this out. So that's the way to read this equation. Okay. So this is simple. So all this comes down to writing out the numbers. So C here is 100 microfarad, or 100 times 10 to the minus 6 farads. RCH is 2 ohms. T is 1 millisecond. And then the maximum, so the operating voltage is 1,000 volts. And then the maximum voltage you can see during this is 10% higher, so 1,100 volts. So these are the data we have in the problem. And then we have K equals to this thing CRH divided by 2T, 1 minus VDC operating max 0.186. Okay, so this is the way this circuit is controlled. So in practice, what we do is you would measure this and measure how long you think the transient will last, and then control the K. And you have a feedback circuit controlling K. Yeah, frequently. There's transients all the time. So this is on quite frequently. Yeah. Good. Right, so that's a good question. So there's 2 factors that comes from. One, there is a max of the max. Right, one, there is a max of max. Then there is the current right now during this transient with a max. So it comes from 2 factors. So the first one is the rate, like the maximum allowed voltage I allow the transient to take, let's say it's 20%. Right? If it's larger than that, I'll open the breaker in the system. Then if it's under that, the breaker wouldn't open. Then but will get passed through to this DC link. So let's say the amount that gets passed through is 10%. Then we'll change this to control that energy. So in reality, what happens is you don't see a constant voltage during a transient. you see a voltage that goes up and down. So this is actually adjusted quite dynamically. You measure the voltage, measure the voltage, track how long this has been, change K a little bit, then measure the voltage again, then change K a little bit. So here for simplicity, you're given the average value. This thing lasts for 1 millisecond. And this sort of the voltage increase we have seen. Sorry?
There's a transient time before the breaker. So I'm assuming this would also be controlled.
No, there's current breakers that open quite fast. That detects current surges. Those will open fast. Yeah. So they're current breakers. So the breakers are designed to operate, but not to be this sensitive. So the breaker will have a level, I'll sort of measure that level, then it will not be quite sensitive. But all of this, there's sort of averaging effect now what's going on here. Right? There's a lot of switching, a lot of averaging that we're not taking into account. So if you really, I guess we don't have a very high power electronics class, but if you look at really people designing high power electronics, be a lot of effort spent on this. How to do detection, how to do measurement, how to do the feedback control, a lot. Okay. Any other questions? Okay, so this is a chopper circuit, right? So this is the one protection we have. The other one we have is again dynamic resistance, which I won't say much about. It's really exactly the same as before. The dynamic resistance hasn't changed from type 1. Hasn't changed since type 1. So again, you add it there to because you want the to get rid of power to this whole stage, right? So there's a fault. There's another way directly to dump power before the first power electronic stage. So that's the exact same equation as before. There, this is not too important what this is. We just have to compute how much, if this is the fault, how much power has to go through there. The same equation as before, we won't deal too much with it. So I guess going back to the it's final cover everything, but the final probably would not cover SDR calculations, right? So that's for one part we're already done. It's just some equations, we already seen it. But the final could cover this because we haven't done this yet. Okay. All right, so give me a second. The Zoom recording cut out again. Try to fix this. Okay, so hopefully this is back now. All right, okay, good. All right, so that was for type 4. So now we want to talk a little bit about type 4 because the equations are so simple. But the generator itself is now very interesting in some regard. But equations are simple enough for us really to think about stability and integration issues into the grid. Okay, so that's some benefit to the simplicity of the equations. Okay. So stability, right, means that, okay, so what does stability mean? Okay, so let's be clear what I mean by stability here. So here's the stability. This is a dynamic, this is talking about the dynamics of the system. What this thing is a disturbance, your system should survive a small disturbance. That's the idea of stability we're thinking about. If something changes in your system, it should still operate. Right? So the dynamics of the system. So this dynamics. Okay, so if you have one turbine, there's two way disturbance I have, right? If the wind changes a little bit, you should still be on. If the load changes a little bit, you should still be off. And a lot of today's challenge, because renewables comes to what small means. Small is changing nowadays. But what is small 20 years ago is not, right? So what is small today was considered large 20 years ago. But today, just because there's so much variability, so the challenge is for expanding what is small means. Okay, so instead of a 0.1% change, can you survive a 1% change? This kind of idea. So where does the stability come from, right? So in power systems, the important thing to remember is in power system, we will always want to do is we want to maintain power balance. Right, so the idea is you want to maintain power balance. You want supply equals demand, or supply equals demand plus losses in the system. So what you want to do is supply equals demand. This is the sort of equation where always that's the goal of the power system operation. So out of these two, right, traditionally there is a big difference between supply and demand, because the typical model is demand is not controllable. Okay, so demand is actually a random quantity in power system. And because this depends on everything that's happening, right? We could, turn off the light in this room, right? I could disconnect the computer. All the things will have some impact on demand. So this is a random number. So this changes all the time. This is random. Okay. And the goal is your supply has to somehow match this randomness. Right? Your goal is to have to match this randomness in supply. All right, so this is the matching problem. This is the tracking problem. You have a target you want to track. Okay? You have a target you want to track. You want to change your generations. You want to change your generators to track this target. That's sort of a very common control problem you have. Think of this, driving a car, you want to stay on the road, for an airplane, all this. This is not that much different. The key difference in power is, that's fine. Okay, let's say I want to track the demand. How do I know the value of the demand I try to track? How does a generator, let's say 1,000 miles from here, know that I changed the demand in this room? So that's where the difference from driving a car becomes, right? You can see the road, you know where you're trying to go. You can track it. Here is, how does the supply know? Like, why would the generator sitting somewhere is for generating power happily? Suddenly, I go turn on the light. Why would the generator now know I need to supply less power or supply more power? Like, what tells the generator to do that? Not the voltage, something else. The voltage doesn't change all that much. So that's the interesting thing about power system control that's different than a lot of other control problems. But you don't know the target. Nobody ever tells you what the demand is. This demand changes stochastically, randomly all the time. And you're asked to track it. Right? So there's something that changes. So the way we do this tracking is the following. As a supply, as generators, you don't know the demand. So of course, when the demand first changes, you don't know it, so you still supply the same amount of power, right? So if demand changes, so a changing demand, this creates a power balance, power imbalance, right? This is a change in energy balance. Because I have more, let's say more demand increases, right? So supply is slightly less than demand. There's this energy imbalance in the system. Where does that come out of, this energy imbalance? Okay. Right, from spinning turbines, right? So what this creates is this energy physically has to come out of somewhere, right? Where does it come out of? What are the storage elements right now that we have? as the spinning turbines, inertia in the spinning turbine. Okay, so what this leads to is a change in generator speed, because you were rotating, let's say, at 60 hertz, happily going along. Suddenly the demand changes. Well, the conservation energy is a physical law, right? That forces energy to come out somewhere. This energy comes out your spinning turbine, okay? And then as a generator, now you know that demand has changed. So the way you figure out demand has changed is you measure your own speed. You're a generator, you measure your own speed. If the system is at steady state, your speed should not change. So now the system deviates from steady state. The way you see it is you will see a change in generator speed. So what does a generator do is the generator tries to maintain a constant speed. Okay, so this is actually how the tracking problem works. As on high level, you want to track supply equals demand. So if you knew instantaneous demand, you can tell which generator what to do to track this demand. You never know that. So the way you figure that out is measure your own physical change. So instead of tracking the demand, when you track it, you track 60 hertz. Okay, so that's why 60 hertz is important number in our system, right? It could be 50, it could be 60, it could be some number. But once you fix that number, you look at that number. That's a target you're trying to track. Okay, so that's a frequency deviation we try to track. So if you in Texas, if you look at last year's blackout during winter, the reason they sort of had a blackout or rolling blackout is trying to make sure the frequency in the system is correct. Right? So the frequency in the system, the generator speed, is the global indicator of how stable a system is. But that is an indirect measurement of the supply and demand imbalance. So that's our goal. So this is actually the power system control and power system dynamics actually requires different way of thinking for traditional control that you may have learned. It's actually different than sort of feedback control and all that. Because fundamentally, you don't get to see the thing you want to meet. Okay, you only get to see an indirect measurement that has delays, right? Because the churning load is seen by all the generators. So the many generators will see the same thing. How do you make sure they all cooperate at that? That's actually a sort of much more difficult problem. It's way outside the scope of this class. But that's sort of the idea we have. Right? So think of supply equals demand means tracking constant frequency. Okay, good. I will not say it that way. No, I will not say we'll have bad inertia, right? The reason is, I would say it's more challenging problem. The reason it's more challenging is because this changing demand shows up as changing speed. This is governed entirely by the conservation of energy. Okay, so nature is helping you out in that regard. Where is your energy stored? It is in the rotating masses. They have to respond to this. You cannot isolate the system, right? This rotating, you have rotating mass. So naturally, you got this feedback signal, you got this frequency deviation. Now imagine your system is entirely, let's say, a type 4 turbine. There is a rotating mass, but that thing sits behind a power electronics conversion station. If you have solar, that thing entirely, there's no mass there anyways, okay? So now how do you respond to a change in the system demand? Right, so that instead of nature giving you this equation, so if you really look at this equation, this is a set physical equation has to do with torque, but that's your classical physics equation. You cannot touch this one. All you can do is track the frequency. If you have renewables, you have stored batteries, electric vehicles, solar, and all that. That still causes energy imbalance. How that shows up to the generator, to the solar panel, that is your problem to design that signal. Okay, nature is not going to provide you that signal anymore. Conservation of energy does not show up in this sort of rotating frame. Okay, so where are the powers? Where are the storage elements in there? We do have storage. We have capacitors, I have inductors, right? For wind, I can dynamically change the pitch. Right? Wind has inertia, wind turbines. Solar, I have capacitor inductors. I can have storage. I have all that things. But those are not following this quantum energy law. Right? You don't have an equation. It's up to you to define that equation. You can define that equation however you want. That's still up to you. We have not figured that out. Okay, so that's the problem. But right now, the way it works is we're going to pretend all these devices are in fact like a synchronous generator. So we'll artificially make your solar panel look like a synchronous generator. Because again, it's electronics, we could do that. But that is not the best use of a solar panel. Right? It's a solar panel, you're making it look like this synchronous generator, which is not a very good job at doing that. Okay? So a solar panel can look like many things. It doesn't have to look like a synchronous generator. But what should it look like? What is the optimal way to do this feedback? That is almost completely open at this point. If you have a grid that's entirely batteries and solar, I come in and turn on a light switch. There'll be some changes in the grid. How should this be reflected at all the generators? How should they respond? That is open. We don't know. So right now, our way is, okay, just pretend we're still all synchronous generators, which is obviously not the optimal thing to do. So they're not. So the way to think about it is solar a worse synchronous generator than synchronous generator? Of course. Is solar inherently a worse device, a less stable device? Not necessarily. We just don't know how to do it yet. We don't know the math yet. That's where really it is. Okay? So this comes down to a nonlinear system that's really hard to control. Through trial and error, we have to figure out how to control one with synchronous generators. We're now doing trial and error again. How to control one with paratronic devices. So that's the way to say. Any other questions about that? So that's a good question. Any other questions about it? So yeah, so there's sort of a lot of things. Renewables has less inertia and not as good. It's a little bit too lazy in that regard. It is not as, because they are not synchronous generators. So of course, they're not as good as synchronous generators. And they're not as good as being synchronous generators. It does not mean they're not as good if you figure out the optimal way to do it. Right? It's just that we have not figured that out yet. Right, but right now, how battery is right? No. So how battery respond? And still, battery thinks it's a synchronous generator. So battery is trying to mimic, like I'm a synchronous generator through its interface, and then that's how I respond. But battery does not have to respond that way. Battery can do income whatever control you want. It doesn't have to pretend a synchronous generator. You just don't know what it is. Like suddenly, if you have all this freedom to design it, we don't know what to do. Right? So part of my work is there. So I do sort of active research. What I do is in that space is how to design these things. Part of Professor Johnson's work is also in that space. Is how to design this kind of thing. So this is a important, and many people are working on this space. If now you suddenly have freedom, what do you do with it? Right? Well, if you say synchronous generator is not, nature doesn't insist you use that, then what model should you have? Those are not far from true. So far from true. And all this comes down to all this power flow equation has a sine and cosine. If there was linear, we would have been done now. It's not linear. So we don't know. Right? So all this is hard. Right? So, but yeah, so I think when you read things like, loss of inertia and all that, it's a bit lazy writing. That's a bit being lazy. Okay. It's not a fundamental issue. It's not like you have no storage. We don't know how to do it. Right? Any other questions? Okay, all right, so good. So stability. So we're going to look at stability in a synchronous generator. This will serve as a, right, so this is a basic concept. But we will not go beyond this, again, because if you go beyond this, everything else, we need a first class control of nonlinear systems, then go beyond this, right? So I think I'm teaching in the fall of this year. I think I'm teaching that class to really go beyond this dynamics. Right. So, but here we're going to look at simple dynamics first. Okay. So the simple dynamics, again, the reason this is simple is you have this nice equation, J omega squared equation. So so let's parse this page and see what it says, right? So it says, okay, well, some input power, some output power. Right? So if everything is steady state, Tm is equal to Pg and nothing happens. If they're not equal, right? If there's an energy imbalance, this energy has to show up somewhere. Right? This energy has to go somewhere. So again, because this is a spinning generator, this is how where the energy goes. Okay, you don't have a choice on this equation. If this were let's say, a battery, you have a choice of this equation, which actually could be better, but makes the math much harder. But here you don't have a choice. Has to go to, this is a rotating machine, has to go to half J omega squared. Okay? There's no choice in this, right? So what you see is, because this is not zero, this energy is not zero, this omega will change. Okay? So this omega will change. That's why you have a change in the speed of the machine. Okay? Right, so a non-zero kinetic energy, changing kinetic energy, resulting in a non-zero change in the angular frequency of the machine. And that is a local measurement you can take. Okay, so again, if this grid demand here changes, you don't know whose demand has changed, you don't know any of that. What you do see is a change in this energy, which shows up as changing angular momentum. Okay, so that you can measure in angular speed. So this is how it shows up. Then the way it shows up is, well, so I have a changing omega. So I have this is a change in the frequency. Okay, this is changing frequency. What does a changing frequency mean? Well, changing frequency will mean a changing your angle of your generator. Right? So your generator has some angle. You can think of this as your angle. So this VA has angle delta. Well, I have a changing frequency, so I have a changing angle. So this delta changes. And the way it changes is precisely delta dot is the changing frequency. Right? So the derivative of the angle is frequency. So if the frequency changes, the angle is forced to rotate. Okay? So if you have, let's say this VA as a vector, then this rotates because you have a delta omega here. You have a non-zero frequency, right? So if it's, so this is according to, right? So if you have a frame of reference that's looking at the synchronous frequency, now you have a difference from a synchronous frequency to be rotating slightly faster or slower than the synchronous frequency. Okay, so your machine, if it was at 60 hertz, will suddenly now not be at 60 hertz. It will be slower or faster. You measure this difference. Okay, so you want the, so this is your imbalancing angle. Right? This is your imbalancing angle. So this has some consequences. Right? So this has some consequences if this changes. Right, so let's say this is positive, right? Let's see what happens when this is positive. So if this is positive, then if you look at this vector, you have a vector of, so IA. Now let's look at what happens to this current through this x-axis. Okay, let's say look at this current through the synchronous reactance. So I have a fixed voltage, right? So this is a machine. Machine is providing a fixed voltage. This speed is changing now, right? This where speed changes. This current, if the speed is increasing, this current will tend to increase. This is what happened to the current. Because you're growing more out of phase, you're close to being 90, getting close to 90 degrees. This is purely reactive. element here. So IA will increase. So IA tend to increase if you have a increasing angle. IA tend to go up. Then if IA increases too much, what happens is, well, you trip a breaker, you trip some protection speed, right? So this can trip protection. Then this generator is out of commission for hours on end, right? If you trip this kind of protection. Okay. So that's why you need to monitor this angle. This is the angle you have to monitor. And from this angle, what you want is, so how do you protect against this? Now you want to change how much power you're putting into the system. Okay? So your goal is, so you change PM to reduce so what do you have control, right? So the grid, the load you cannot control. So changing load will show up as a changing your generator. If you don't deal with it, well, eventually something will trip in your generator. Okay? You have some current that's running away from you. So what you can control in your generator is let me change my mechanical. How? Okay, to balance out this equation. Basically, you want to balance this equation out. Again, this you have no control. This you have control. So control the PM. Now you can to make that difference 0. Okay, so that's the idea you want. And this actually leads into stability. So let's look at how power flow enters into this picture. So again, if you look at power flow, as you remember the calculation we did from before is we have the power you send to the grid, X sine delta, right? This is the amount of power you're sending to the grid. And then we have a system maximum, right? So we have a maximum in the system. So the way to think about this is, well, I can change my delta to match the power to the grid. I can change my delta to match power to the grid. So I have PG is I is V out prime VG X delta I. Okay. So there are some points where you cannot meet. Okay, so there are some points that's impossible. You can never operate at this point. Right? You can never operate at this point. But anything along this curve is possible. Anything along this curve is possible, right? So PM is your input power here. So the reason that you want to stay on this side of the curve and not this side is, can be seen and looking at what happens. Let's say you pick an operation point here. That's your PM. Okay. So let's say if you want to, let's say you're asked to give more power. The way you do it is you can increase your angle a little bit, provide more power. Okay. If you ask to provide less power, decrease your angle a little bit, right, to provide less power. Now suppose you're stuck on here. Then you have the relationship goes the other way. Right? So if you're stuck on this red point here, so here is you increase your power, right? So this is increasing power, this decreasing power. On the red dot, the opposite happens. If you're asked to increase your power, you have to decrease your angle. You're asked to decrease power, you have to increase your angle. So you have a different sign on the feedback controller you have. You have a different sign on the feedback controller. This will confuse your controller if you can operate at both ends. Because your controller sees this, say, hey, look, which way should I go? Right? To increase or decrease my angle of operation, I need to know, am I on the left or on the right? Okay, right? Because this requires different ways of changing my active control. So we need to pick a side to operate on. So you have to pick a side to operate on. So we're going to pick on the left side. Because we want to say that If you operate on the left-hand side, there's a different way of how you should control this. If you allow to operate on both sides, we don't know how to control it. We don't know how to control it. Yeah.
Maybe instead I
Right.
What if we have two controllers and one will activate level one first three and then the other controller can be activated at the second time?
Right. So that is no, that's not a good idea, because when you measure this angle, right, this is with reference to what? To the grid, right? This is with reference to the grid. Okay. How do you measure the angle, right? So can you measure the angle with reference to the grid? What kind of measurement do I? So if I only take my local measurement, I don't know what the angle at the grid is. I don't know the grid angle. Okay. So I only get one angle measure. An angle is a relative quantity. So to measure my angle, I need to be referenced to something. We're referencing to the grid itself, right? So actually, I don't know. From local measurements, I cannot tell which side am I. I don't know. I don't know the grid angle. I cannot do the subtraction. So I better make sure that whatever happens, I'm on one side. That's the idea. Right? I can't tell. This is the local information. Okay.
Is there some advanced stability without a feedback controller? Because if you just have the delta negative
Right.
changes, like you're already getting, yeah, but if there's some relationship between like this change in angle that's happening to the grid and then you're not power. Is that power is that stable by itself?
No, you need a feedback controller, because if you have a generator, you need to increase your power source or decrease the amount of power you're putting into the generator, right? Let's say you have a coal generator, or you have anything that boils water. So fundamentally, what happens is you need to open and close a valve of the steam that goes into the turbine. That requires a feedback controller. Now that's a mechanical controller that you have to control. Right? So that you have to have some kind of feedback loop to the inner power going into the generator. That you need that. Right? So you still need some sort of feedback mechanism to make sure this works. But just that angle is a relative quantity. You don't know the other process angle. Like you don't know what the angle right now is at ECE building. Not a question. We don't have that measurement. So you want to make sure that you always pick one side and stay on this side. Okay. Right. So we'll go through this for much more detail next class. We'll look at stability. But the idea for stability is again sort of, make sure you operate on this side. We'll do a bunch of questions, to see sort of how much this change will be. And often your limit is such that you don't even to come close to this pi over 2 point. So often you have a limitation that the angle has to be, say, less than 40 degrees or something. Right? So that's a lot of times what the transfer limit is between. Right? So we'll stop here today. Next class we'll continue with this. And after that, we'll sort of step back from the physical generators and start looking at probability. But for now, we'll have sort of constant wind speed and all that. Then we'll deal with what happens when the wind speed is not a constant.